Hi friends, in this video I will explain you about two types of elementary signals. In the last video I have explained you about three types, and again I will discuss about two more types of elementary signals in this video. The first one is unit impulse function. The first one is unit impulse function. The unit impulse function is also called as Dirac delta function. The unit impulse function is also called as Dirac delta function. It is denoted by delta of t. It is denoted by delta of t. We can write mathematical equation as delta of t is equals to 1 for t is equals to 0 and 0 for t not equals to 0. The mathematical expression of unit impulse function is delta of t is equals to 1 for t is equal to 0 and 0 for t not equal to 0. The area under the curve is unity. This is the important point in this. Area under the curve is unity. Let us see the signal diagram. Here the area under curve is unity, and at t is equals to 0, delta of t is 1. Next, let us see delayed unit impulse function. Till now we have discussed about unit impulse function. Now let us see delayed unit impulse function. In delayed unit impulse function, the mathematical expression is delta of t minus a is equals to 1 for t is equals to a and 0 for t not equals to a. Delta of t minus a is equals to 1 for t is equal to a and 0 for t not equal to a. Let us see the signal diagram. Suppose this point is a, this is 0, this is a. Actually it should be at here, but it is shifted towards a, and at a the value is 1. So this is about delayed unit impulse function. Next, let us see unit impulse as a pulse. Unit impulse as a pulse. Now let us discuss unit impulse as a pulse. For this, first I will show you the signal diagram. Generally we discuss that the area under the pulse is unity. It means, for example, if the width is delta, then the length should be 1 by delta. Or if the width is 1 by delta, then the length should be delta. We know that generally area is equals to L into B. Let us consider L is equals to 2. Here it is given that A is 1. So 1 is equals to 2 into B. So B is equals to 1 by 2. So length is nothing but inverse of width, or width is inverse of length. This gives area under pulse is unity. There are 4 conditions for this. First one is width of pulse is 0. Width of pulse is 0. Height of pulse goes to infinity. area under curve is always unity. First one is width of pulse is 0. Second one is height of pulse goes to infinity. Third one is area under pulse or area under curve is always unity. Next one, height of arrow indicates total area under impulse. Height of arrow indicates total area under impulse. This is about unit impulse function. Unit impulse function is denoted by delta of t. The area under this pulse is unity. Here the width of pulse is 0 and height of the pulse goes to infinity, and area under curve is always unity. The relation between unit impulse and unit step function is defined as u of t is equals to integral minus infinity to infinity delta of t dt, or we can also write it as delta of t is equals to d by dt of u of t. U of t is equals to minus infinity to infinity in delta of t dt, and delta of t is equals to d by dt of u of t. Now let us discuss about discrete time unit impulse function, which is also called as unit sample sequence function. In discrete time unit impulse function, in place of t we have to write n. That's it. That is the change that we have to do in it. Consider delta of n here. Delta of n is equals to 1 for n not equals for n equals to 0 and 0 for n not equal to 0. Delta of n is equals to 1 for n equals to 0 and 0 for n not equal to 0. Let us see the signal. This is delta of n. Next, let us see shifted version of unit impulse function. Shifted version of unit impulse function. It can be written as delta of n minus a is equals to 1 for n equal to a and 0 for n not equal to a. Let us see the signal for this. 0 a it will be like this, delta of n minus a. This is about unit impulse function. Next one we will discuss. This is about unit impulse function. Sinusoidal signal. The mathematical expression for sinusoidal signal is x of t is equals to a sin omega t plus phi, where a is nothing but amplitude and omega is angular frequency. Omega is angular frequency and phi is equals to phase angle. Now let us draw the signal and we will compare them. Zero. Now let us see this. Here this signal is starting somewhat late. Actually the signal should start at 0, but it is delaying. It is starting somewhat late with a phase angle phi. So it can be written as A sin omega t minus phi. Here this is the correct signal with it is starting at 0. So it is A sin omega t. If you consider this signal is starting somewhat earlier. It is starting in advanced state. So it is A sin omega t plus phi. So these are the three types of signals. A sin omega t, it means phi is equals to 0. Next, A sin omega t minus phi. Other one is A sin omega t plus phi. Phi greater than 0, phi less than 0. This is about sinusoidal signal. The general mathematical expression for sinusoidal signal which is continuous is x of t is equals to A sin omega t plus phi. For example, if it is a discrete